Okay, so our textbook derives the pressure put on a plate or on some sort of two-dimensional side by taking the weight density of water. I have trouble with that Greek letter. Times a function for the width of the side times a function for the height of the side. Okay, so let's draw what we're dealing with. We have a trough, which is something like this. This should be farther. I have trouble with visualizing, with drawing a 3D object in 2D. Huh? That's my trough, but then this is the side that we're talking about. This is where the water is being put pressure on. So we need to come up with a width function and a height function. And so if we were to superimpose this on an x and y axis, it'd be kind of hard to find the width function because it starts right in the middle. So instead, let's flip this. Now it's a little easier. I think you could do this with respect to the x-axis. I think the easier way, though, is to consider the y-axis our variable of integration. How high is this thing? This thing is 6 feet. So we could integrate from 0 to 6. The weight density of water is 62.4. So as it goes in here. The width I haven't determined yet, but it's going to be in terms of y because I'm saying my height is my variable of integration. So that's how my height varies. So now we need to come up with a function for this width based on where we are on the y-axis. We know that this is 7 across, and so we could use the idea of similar triangles. The big triangle here is this one. This is 6 on the side, and this is 7 cut in half. So this is 7 over 2. And then as we're moving up for our width function, the triangles are going to be shrinking, right? So we have a smaller triangle with y on this side, depending on where we are on the y-axis. And then this over here is something we haven't determined, so I'll call this x. X might be confusing, and w might also be confusing because it's not the entire width. We'll just say j. Okay. So I want to create a function for j because j will be half of this width. I'll just double whatever j is, and that will be our width function. All right, so j, let's see. Oh, how do we relate these two? So I'll take the bigger triangle side, this vertical side, divide by the smaller corresponding side. And that should be equal to the bigger triangle side, divide by its corresponding side. And then we could simplify the right side a little bit. 7 over 2 divided by j. That's the same thing as 7 over 2 times 1 over j, so that's 7 over 2j. And I'm trying to get j by itself because j is dealing with the width, right? So I'll multiply 2j to both sides, so I get 12j over y equals 7. I'll multiply y to both sides, and then I'll divide both sides by 12. So j is going to be 7 over 12y. So that's what this extra helper variable is. The width is double that, right? So the width would be 2 times this fraction, so it's 2 over 6y. But there's one little problem, because at y equals 0, it would say the width is 0, right? So I just need to make an adjustment. The width is 7 minus this fraction. So now we're ready to integrate. So this is 7 minus, this is 7 all the way across. Okay, so it's 7 minus 7 over 6 y times y dy. Okay, I think that's it. The hardest part's done. I'll probably leave the rest of this because I got a few other videos to make, but this is, I distribute that y to everything, so this is 7y minus 7 over 6y squared, and you can take it from there for finding the antiderivative, and then plug in your limits of integration.